Hi KCET 2025 aspirants, hope all of you are doing really well and preparing very hard for your KCET examination. So today in this video we are going to do the one shot of the chapter Thermodynamics. So do not worry, this is a very easy chapter. You just need to focus on certain formulas and then definitely you will be able to solve the questions. Okay, so let's see what all things we have in today's class. So the first thing, that is thermodynamic terms, second applications, third enthalpy change of a reaction. Okay, next I have spontaneity, types of enthalpy, Gibbs free energy and KCET PYQs. Okay, so I have included the previous year questions also in this video so that we can have an understanding that what exactly we have studied, can we apply that to the questions or not. Okay, so let's go to the first thing, weightage. You can see consistently one questions have been asked from this particular chapter, so definitely you can easily score this 1 mark. Okay, so now coming to thermodynamic terms, what all things we have. So let's go and discuss this part. So first of all, what is system and surrounding? So system means anything which is where your reaction is happening, which you are observing, that is your system. Okay, apart from that particular thing, the rest whole thing comes under surrounding, and system plus surrounding will give you universe. Not a very important topic, so we'll go to next, types of system. This is important. We have 3 types of system: open, closed and isolated. In open system, what happens? We can exchange both energy and matter. Okay, in case of closed system, we can exchange only energy. In case of isolated system, neither energy nor mass can be exchanged. Neither energy nor mass can be exchanged. Okay, now what happens here? I'll give you an example. So here we can have an example where I am boiling water, okay, in an open container. You are boiling water in an open container. So water particles will evaporate and go out. So there is an exchange of matter, and energy also it is lost. So that is also exchange of energy. Now when in closed system, exchange only energy. So here you can have, for example, you have an I can say, suppose you are having a closed lead container, okay, and you are boiling water here. Okay, so you have closed this container, so the water molecules cannot evaporate or cannot escape from this container. So here there is no exchange of matter, only there is exchange of energy. And the same third is if you take a thermo flask, right? So you know, in thermo flask the heat energy cannot enter or cannot release out, and even the matter cannot be exchanged. So this is an example of isolated system. Next, what is state of a system? So see, state of a system is used to define the condition of a system. Okay, at what state the system is there, and how can we explain the state of a system? Pressure, volume and temperature. Okay, next, now, so okay, just a minute. Yes, now coming to something called as internal energy. Okay, so now we are explaining different thermodynamic terms. So the next term here is internal energy. Internal energy is what? Total energy of the system. Okay, in a system there are different types of energies like kinetic energy, potential energy, rotational energy, vibrational energy. So the summation of all these energies together is called as the internal energy of a system. Okay, now how can we change the internal energy of a system? By work or heat. Okay, so if you do some work on the system, or if you provide some heat, if you provide some matter, we can change the internal energy of the system. Now it is a state function. Now what is a state function? State function means it depends only on the initial and final values. Okay, that is the meaning of state function. State function means, suppose you had the system at one particular state, you added some heat, and then the state of the system changed, right? So the state of the system changed, but it does not depend how you added heat. Like, did you add the heat by doing some work on it? Do you added some heat by giving like I can say temperature to it? So how if you are doing mechanical work, if you are doing electrical work, so it doesn't depend how you have changed the system. It only depends on the initial state and the final state, not the process. So that is why it is a state function. Okay, so delta U is equal to U2 minus U1. Now here I will tell you something about the first law of thermodynamics. Oh, just a minute. Okay, here I have, okay, just a minute, yes. Okay, now if you see in internal energy, what is the formula of internal energy? Delta U is equal to Q plus W. Okay, please remember this, we will explain in the next few slides also. Delta U is equal to Q plus W, where Q is your heat, okay, and W is your work, right? So by heat or by work we can change the internal energy of a system. Now if the system, if the process is an adiabatic process, okay, what do you mean by adiabatic process? Adiabatic process is that process where Q is equal to 0. Then what I will get? Delta U will be equal to W, right? So that is given for an adiabatic process, delta U is equal to W. Now next, if I see here, so for internal energy, as I told you, delta, if in this delta U is equal to Q plus W, okay, if in certain case work is equal to 0, then what will be equal to delta U? Delta U will be equal to Q. Okay, when will this be possible? When we have work is equal to 0. Okay, now coming to, okay, so now you can see internal energy can be changed by both heat and work. Okay, now delta U is equal to Q plus W. So I just want to tell you here about the sign convention. If you see, I have written here sign convention about heat. So if Q or heat is added to the system, okay, then it is positive. If heat is removed from the system, then it is negative. Okay, if heat is added to the system, it is positive. If heat is removed, then it is negative. Next, similarly, if I have for work, okay, so work, what is the sign convention for work? If work is done, see, very important, if work is done by the system, then it is negative, and if his work is done on the system, okay, then it is positive. Okay, work is done by the system, then negative, work is done on the system, then it is positive. Now before moving to that, I want to discuss something called as types of processes. So how many types of processes we have? So generally we have 4 types of process. One is your isothermal process. Next we have isochoric process. Then we have thermal, isochoric, isobaric process, and I have adiabatic process. So adiabatic process just now I discussed with you. So in isothermal process, what happens? Change in temperature is equal to 0. In isochoric process, change in volume is equal to 0. In isobaric process, change in pressure is equal to 0. And in adiabatic process, Q is equal to 0. Clear? Now what is there? If I see, one more thing that I want to add here is, in case if the process is isothermal, then delta U will also be equal to 0. Please remember, this is a very, very important relation. If your isothermal, if the process is isothermal, then internal energy will be equal to 0. Okay, change in internal energy will be equal to 0. Okay, fine. Now we have discussed, so internal energy is 2 things. It is determined by your heat and work. What is the sign convention for work? Work is done by the system, then it is negative, on the system, then it is positive. Next, internal energy is also determined, as I said you, by heat. Okay, so if heat is added to the system, then it is positive. If heat is removed from the system, then it is negative. Okay, now coming to general case. Okay, now here's a question: express the change in internal energy of a system when no heat is absorbed by the system from the surrounding, but work is done on the system. What type of wall does the system have? Now see, there is no heat is absorbed by the system from the surrounding. Okay, but work is done on the system. So I have this formula, right? Delta U is equal to Q plus W. Now here no work is there, so that means Q, no heat is there, that means Q is equal to 0. Work is done on the system, so W will be positive. Okay, now you can see if no heat is absorbed, then what type of wall will be required? For this we need adiabatic wall, otherwise heat transfer will take place, right? Because there is no heat exchange between the system and the surrounding, so we need a adiabatic type of wall. Now second one, no work is done on the system, but Q amount of heat is taken out from the system and given to the surrounding. So I have delta U is equal to Q plus W. I'll write the general equation here. Heat is removed, right? So it is minus Q, right? The delta U will be equal to minus Q. And what type of wall? Because there is an exchange of heat between the system and the surrounding, so we call it what? We will call, what type of wall does the system have? The system have a, I can say, means you can say an isothermal wall. Okay, so whenever there is an exchange between the energies or between the system and the surrounding, we can just say that, oh sorry, one second, yeah, so this value was your delta U was equal to, how much we got, work is delta U is equal to W here, delta U is equal to minus Q here, okay, and the wall I can say non-adiabatic wall. Okay, means where we can exchange the heat. Okay, next, W amount of work is done by the system and the Q amount of heat is supplied to the system. What type of system it would be? So if you have delta U is equal to, you are giving W amount of work is done by the system, that means minus W, right? Minus W, and Q amount of heat is supplied to the system, that means plus Q. So minus W plus Q will be your internal energy. Okay, understood? Fine. Now we will go to next, what is your work? So what is the formula for work? You should be remembering, from here questions will be asked. So work done formula for an irreversible process is minus P external V2 minus V1, and for a reversible work done process it is minus 2.303 nRT log V2 by V1. This is isothermal reversible process. Okay, isothermal reversible process, if that is given, work done formula is this one, or else in general the work done formula is this one. Now there is one more case, that in case of free expansion, means if some gas is doing work in case of vacuum, okay, where there is no atmospheric pressure, in that external pressure becomes 0, that means work done is equal to 0, and if you know delta U is equal to Q plus W, right? Delta U is equal to Q plus W. Now work done is 0, so delta U will equal to Q. Okay, okay. Next we will see here, so in isothermal process, as I said you, temperature is constant, so delta U will be equal to 0. Okay, delta U will be equal to Q plus W is equal to 0. This is again a very important relation. Next, so in that case, if your delta U is equal to 0, then I can say Q is equal to minus W, or I can write Q is equal to, this is minus and W formula is minus P external V2 minus V1, so we will get plus P external V2 minus V1. Okay. Next, isothermal reversible work done, in the same case you can see Q is equal to minus W, so this minus is there and W formula is again minus 2.303, so minus minus will become plus and we will get this particular formula. Okay. Now in case of adiabatic, what happens? Delta U is equal to Q plus W. In adiabatic process Q is equal to 0, so delta U will be equal to W directly. Okay. Next, coming to enthalpy. So enthalpy, heat exchange at constant pressure, is called as enthalpy, and it is also a state function and it is denoted by delta H. Okay, we have two formulas here, delta H is equal to delta U plus P delta V and delta H is equal to delta U plus delta Ng RT. Now what is this delta Ng here? That is your number of gaseous moles of products minus number of gaseous moles of reactants. Okay, and R is what? R is your gas constant. okay, and T is temperature. Clear? Okay, next I have here delta H is exothermic. If delta H is negative, then it is exothermic. If it is positive, then it is endothermic. Okay, clear? Fine. Next, at constant volume. So if you see at this formula, delta H is equal to delta U plus P delta V. If volume is constant, okay, if volume is constant, that means delta V will be equal to 0, right? So I can write delta H, delta V will be equal to 0, that means this whole term will become 0, delta H will be equal to delta U. At constant volume, delta H is equal to delta U. Okay, and if you remember, delta U was equal to Q plus W, right? And since volume is constant, this work done is also 0, so delta U will be equal to Q. I can write like this, QV denotes that is it is a constant volume system. Okay. Next, what is extensive and intensive properties? So extensive properties are those properties which depend on the amount of substance present. Okay, depends on quantity. For example, if you see yes, so for example, if you see mass, right, 1 gram mass is different, 5 gram mass is different, volumes are, these are all depends on the quantity. But if you see temperature, density, pressure, molar volume, molar specific heat capacity, these are those things that do not depend on the amount of substance, it is a fixed value. Okay, does not depend on the quantity. Next, we have heat capacity. So heat capacity, we have three types. What is your heat capacity? Molar heat capacity and specific heat capacity. So see, heat capacity means suppose you have been given with any amount of water or any amount of any substance and you are raising its temperature by 1 Kelvin or 1 degree, then we call it as heat capacity. Specific heat capacity means when you have 1 gram of any substance and you are raising the temperature by 1 degree. Then molar heat capacity is means when you have 1 mole of a substance and you are raising the temperature by 1 degree. Okay, clear? So now if I see, so you can see amount of heat required to raise the temperature by 1 unit, amount of heat required to raise the temperature of 1 mole of a substance by 1 unit, amount of heat required to raise the temperature of 1 gram of a substance by 1 unit. Okay, so now here you can see Q will be equal to C into delta T, and for molar heat capacity it is Cm into delta T, and for specific heat capacity is Mc delta T. Okay, that is how we denote the formula. Next, the relation between Cp and Cv. So what is your Cp and what is Cp? See, Cp is your heat capacity at constant pressure, and Cv is equal to heat capacity at constant volume. Okay, now if you see that, I can write Q is equal to, just now we wrote the formula, right, Cp delta T. Okay, just now we wrote this formula, C delta T. Okay, now if I am saying that the heat, the pressure is constant, then I can write this one as Qp. Okay, now Qp is nothing but delta H. So I just told you enthalpy is the heat exchange at constant pressure. So delta H by delta T will be equal to Cp. Please remember this formula. Okay, now similarly I can also say that if it is a constant volume system, Qv will be equal to Cv into delta T, and I can say that Qv by delta T is equal to Cv. And what is this Qv? Heat exchange at constant volume, and heat exchange at constant volume is delta U by delta T. Okay, so I have two things that I should be knowing. Heat exchange at constant volume is delta U, heat exchange at constant pressure is delta H. Okay, next I have here, so easily see how I am getting this equation, Qv. So I can write Qv is equal to Cv delta T, Qv is equal to Cv delta T. Okay, and here we have, and Qv is nothing here, delta U. Similarly, I can write here Qp is equal to Cp delta T and Qp is equal to delta H. From here only I can derive that Cv is equal to delta U by delta T and Cp is equal to delta H by delta T. Okay, so please remember this equation, it will be used later. Next questions, which of the following properties cannot be used to describe the state of a system? State of a system is described by pressure, volume and temperature. Universal gas constant cannot be used. Next, when work is done on the system or by the system, there is a change in internal energy, right? We can change the internal energy of a system by doing work or by work and heat. Okay. Next, in an adiabatic process, the work done is 50 kilojoule. What is its internal energy? Okay, so if you see delta U is equal to Q plus W. Work done is adiabatic process means Q will be 0. Work done is 50 kilojoule. So delta U will be 50 kilojoule. Okay, very simple question. An open system allows the transfer of both energy and mass. Okay, now we will go to the next segment where we will be talking about enthalpy, and this is where from most of the questions will be asked in the examination. Okay, so first of all, enthalpy change of reactions. So what happens, what is standard enthalpy of a reaction, what is enthalpy change during phase transformation, enthalpy of formation and Hess's law. We will see these things. And types of enthalpy, enthalpy of combustion, atomization, bond enthalpy, lattice enthalpy, enthalpy of solution. Okay, so let's start with the first thing, that is standard enthalpy of a reaction. Now whenever there is a reaction happening, there is an involvement of enthalpy, means where either energy is released or energy is consumed in that particular reaction. Okay, so enthalpy change accompanied by a reaction is called as the reaction enthalpy, and enthalpy of a reaction is equal to the total enthalpy of products minus total enthalpy of the reactants. Okay, and here something which we should be knowing is, if delta H is negative, means if this value products minus reactants comes out to be negative, then it is an exothermic process, and if it is an endothermic, if it is a positive value, means products minus reactants is positive, then it is endothermic process. Okay, next we see standard enthalpy of a reaction. So I told you that whenever we have any reaction, we are either some energy is released or consumed, and that is called as the enthalpy of a reaction. But if the same thing, means if the reaction is happening under standard conditions, what do you mean by standard conditions? That means if the pressure is maintained, I think I have mentioned it. Okay, standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances are in their standard state. Means the elements are in their standard state and the temperature is your 273 Kelvin and pressure is 1 bar. So if that reaction is happening in under standard conditions, then the energy released or consumed in that particular reaction will be your standard enthalpy of reaction. Okay, so the standard state of a substance at specified temperature is its pure form at 1 bar. So pressure is 1 bar, and whatever substances are present at that time, that is called standard enthalpy. And how do we represent standard enthalpy? Delta H naught. Okay. Next, I have here certain enthalpies during the phase transition. So enthalpy of fusion means when 1 mole of a solid changes to liquid. So it is represented as delta H fusion. Then delta H of vaporization, liquid to vapor. And sublimation, directly from solid to gas when the change is happening. At that time, what is the energy required or consumed involved? That is your sublimation enthalpy. Okay, phase transition enthalpies. Next, what I have? Okay, next I have standard enthalpy of formation. This is very important concept here. See, the standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable state is called as standard molar enthalpy of formation. Now, for example, I want to ask you that if water is formed, what is its enthalpy of the reaction? What is the enthalpy of the formation of water? So for that we need to have a reaction, right? So what should be the reaction? Whenever you write enthalpy of formation, the product should always be 1 mole. Means we should always count for the formation of 1 mole of a substance, and it should form from the native elements. Means hydrogen, what is the native state of hydrogen? Like this, and oxygen is half O2. for balancing I will write like this. So this reaction represents the formation of enthalpy, formation of water. Okay, this reaction shows me the formation of water. Now for example, I can also write, for example, for carbon dioxide, if I want to write the reaction of formation. So carbon and oxygen should be in its native state. Okay, I cannot write this reaction. See, this reaction will also give me carbon dioxide, but this reaction is not the formation reaction. Why? Because the elements are not in the standard state. I have to take always the elements in the standard state. Now at this point of time, whatever energy is released, that is called as your standard enthalpy of formation. But two things you have to keep in mind here, that always 1 mole of a product should form and the elements should be in their standard state. Okay, next, how it is denoted? Delta F H naught. Okay, now coming to Hess's law. What is Hess's law saying? See, if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reaction into which the overall reaction can be divided at the same temperature. Very complicated statement, but the simple thing is, if a reaction is there, okay, if a reaction is there and it is occurring in 3-4 steps, then the sum of this 3-4 steps, the enthalpies involved in this 3-4 steps, addition of that will be the enthalpy of the final reaction. Like for example, if I have A plus A gives me B, B gives C, C gives D, and the final reaction is A gives D. So the enthalpy of this reaction will be the addition of the enthalpies of these reactions. Okay, so that is your Hess's law. Next, if I see a thing like this, so A is giving me, this is the enthalpy of the reaction. Now it occurs in 3 steps. So delta HR here will be equal to delta H1 plus delta H2 plus delta H3. Okay. Next, we will have something called as enthalpy of combustion. So whenever we have when 1 mole of a substance undergoes combustion, means undergoes reaction with oxygen to form a product, that is called as your enthalpy of combustion, and in this case energy will always be released. So enthalpy of combustion is always negative, or you can say exothermic. Clear? Okay, next what I have, okay, just a minute, I will erase that. Yeah. So here's a question from Hess's law, which is a very important question. Calculate the heat of combustion of ethane. Okay, so the reaction is what? You have to calculate the heat of combustion of ethane. Reaction is already given to me, where the heat of formation of ethane gas, carbon dioxide gas, water liquid are respectively these values. So you have been given with the formation of all, and we want to calculate the enthalpy of this reaction. So if you remember, enthalpy of any reaction is what? The enthalpy of reactants summation minus the products minus the enthalpy of reactants. So here what all things I have in the reactants? Water and carbon dioxide. So see, so what will be the formula? The formation, so I have 3 times, okay, 3 times the formation of H2O. Okay, then I have 2 times the formation of CO2. Okay, this is there, minus C2H6. So 7/2O2, see, this is because it is found in the native state. So here what I can say, because it is native state, enthalpy of formation becomes 0. So here I have enthalpy of formation of what? C2H6. Okay, so now I can see the values. If I write for carbon dioxide, it is minus 84.7. okay, then sorry, for ethane it is minus 84.7. okay, for carbon dioxide it is minus 393.5. okay, then for H2O, it is minus 285.8. Okay. So now if I substitute the values, so for water it is how much? 3 times of minus 285.8, okay, plus 2 times of, I have carbon dioxide minus 393.5. Okay, I will check the values once again. For ethane it is minus 84.7, carbon dioxide minus 390.5, and for water it is minus 285.8. Yes, so this is the enthalpy of the products. Then minus enthalpy of the reactant, that is C2H6, which is minus 84.7. Okay, so you can see all the units are in kilojoules, so no need to worry of anything about unit conversion. So we have to solve this. Okay, so if you solve this, you will find the answer to be minus 1559.7 kilojoule per mole. Okay, check the calculation once, simple addition and multiplication, you can do this calculation, but answer will be A. Okay, next we talk about enthalpy of atomization. So it is the energy required to break 1 mole of a bonds to get atoms from a molecule, that is called as your enthalpy of atomization. Okay, next bond enthalpy. So see, bond enthalpy means what? The change in enthalpy when 1 mole of a covalent bond of a gaseous covalent compound is broken to form products in the gaseous phase. So when the molecule is in the gaseous phase and you provide some energy and breaks all its bonds, and the products or the ions formed are also in the gaseous phase, that is called as your bond enthalpy. Now what is average bond enthalpy? So average amount of energy required to break 1 mole of a bond of a specific type in a chemical compound. Okay, so average means when you have more than 1 bonds, okay, and you just divide. For example, if I tell you CH4, suppose I give you an example. Yes, suppose CH4 is there, right, and I tell you to break or to get this one, the value was, total energy was 1665 kilojoule per mole. Okay, so that means what was the enthalpy or what was the energy required to break 1 CH bond? So that will be 1665 divided by 4. Okay, you will get the average enthalpy here. Next, you can see, for example, first I will bring CH4, right? CH4 first, if I break, it is CH3 plus H. First step I will get this much energy, next step this much, next step this much. So these are the different steps in which the hydrogen, this process will happen, right? So if you see the addition, the average means, that means what is the average bond of a CH bond, then you have to take the total energy divided by 4, that is 416. Okay. Next we have here delta. So enthalpy of a reaction can also be calculated in terms of bond enthalpy. Okay, so it is always bond enthalpy of, so here I have done mistake, bond enthalpy of reactants, okay, minus bond enthalpy of products. Please correct this one. I'll write it again. Delta H of a reaction, if bond enthalpy is given, then it is bond enthalpy of reactants minus bond enthalpy of products. Summation I am writing. Okay, so total bond enthalpy of reactants minus total bond enthalpy of products will give you the enthalpy of a reaction. Clear? Okay, now question is there, calculate the carbon-carbon double bond energy in ethane from the following reaction. Okay, so we have been given with this reaction, you have to find the carbon-carbon double bond reaction. Okay, fine. So how we have to do? Delta H of the reaction is already given. So I know that delta H of the reaction is equal to bond enthalpy of reactants minus bond enthalpy of products, right? So here what all bonds will break? See, if I draw this structure, it is like this. Okay, it is like this. So what will happen here? The bond enthalpy between CH bond will break, CC bond will break, right? So how many CH bonds will break? 4 CH bonds will break. So for CH bond, how much energy is required? Yes, 4 times of 436, right? So I will write first one, 4 times of 436. Next, there will be 1 CC bond will also break. So that value we have to calculate. So let it be X. Okay. Next, what I have to break? Hydrogen molecule, means HH bond I have. Okay, 1 second. CH is 412. I made a mistake here. This is 412 plus X, right? Then this bond broken, minus I have to break hydrogen bond. Hydrogen is how much? Hydrogen HH bond is 436. HH bond is 436 minus bond enthalpy of the product side. So product side you are again having CH bond, 6 CH bonds are present. So 6 into 412, okay, and then you have to break this CC bond also, so plus 348. Now these all things will be equal to minus 138. So let me just solve this part first, then we will go to that one. So 4 2s are 8, 4 1s are 4, 4 4s are 16 plus X plus 436 minus, I have this one is 6 2s are 12, 6 1s are 6 plus 1 7, 6 4s are 24, 6 2s are 12, 6 4 24 plus I have added this 348. So how much it will be? 8 plus 2 10, 7 plus 1 8 plus 4 12, 4 plus 3 7 plus 1 8, then 2 2820, right? 2820. Now let me solve this part. How much I will get? 1648 436, that is 8 plus 6 14, 437 plus 1 8, 6 plus 4 10, 2084, okay. 2084, then I have 2820 and 2084. I have to subtract this one, right? So 10 minus 4 6, 11 minus 8 is 3. This will give me 7. Yes, so minus 736 I got. So I can write this one like this. This whole value came out to be minus 736 plus X is equal to minus 138. Okay, so minus, I can take this 736 on that side. So 736 minus 138. So 16 minus 8 is 8. 12 minus 3 is 9, and I have 6 minus 1 is 5, right? So something 598 kilojoule per mole, option number D I will get. Okay, I hope this calculation is clear. Next, what is lattice enthalpy? So lattice enthalpy is the energy required when you break a solid, a ionic solid, so that the ions are produced in the gaseous state. Okay, so that is your lattice enthalpy, and to calculate lattice enthalpy we need this Born-Haber diagram. Directly lattice enthalpy is not calculated, but using Born-Haber's process it can be calculated. Okay. Next, enthalpy of solution is equal to lattice enthalpy plus hydration enthalpy. So you should remember this formula. If the values are given, solution enthalpy is your lattice enthalpy plus hydration enthalpy. Means when you have an AB solid and you are dissolving it in the aqueous medium, right? So that is your enthalpy of solution. But first this has to be broken into the gaseous ions, so that requires your lattice enthalpy, and now this gaseous ions are converted to aqueous ions, and that requires your hydration enthalpy. So now this total enthalpy of solution is equal to lattice enthalpy plus hydration enthalpy, and this is only nothing but your Hess's law, which says that if a reaction occurs in 2 steps, the enthalpy of their reactions can be added. Okay. Next, we'll do some questions. On the basis of thermochemical equations A, B and C, find out which of the algebraic reactions given in options 1 to 4 is correct. Okay. So if you see what all reactions I can find, Z is equal to X plus Y. So if I add X plus Y, we can check through options, that will be more clear. So if you see, if I add these 2 reactions, will I get this reaction? No, because if I add these 2, I will get 2 carbon, and there is no 2 carbon here. So this is a wrong relation. Now it is given X is equal to Y minus Z, means if I subtract these 2 relation, will I get this one? So if I subtract these 2, then I should have carbon monoxide term, right? If you add these 2, carbon monoxide will be cancelled, but if I subtract these 2, carbon monoxide term has to be there, which is not there. Next, X is equal to Y plus Z. If I add these 2 reactions, will I get the first reaction? You can see CO, if I add these 2 reactions, then CO and CO will get cancelled. Half O2 plus half O2 is 1 O2, I have carbon and I have CO2. So yes, definitely if I add B plus C, I will get A. So I can write X is equal to Y plus Z. So 3 is the correct answer here. Okay. Next, consider the reactions given below. On the basis of these reactions, find out which of the algebraic equations given in 1 to 4 are correct. Very similar reaction. You can see here that this reaction and this reaction, what is the relation? Here it is given x kilojoule per mole, here it is y kilojoule per mole. Okay. Then what else is there? Okay, here you can see that this is in the native state, right? But here what is done? Here we have broken this, means here some enthalpy of atomization is involved to break this one. So here definitely more amount of energy is involved, because directly hydrogen is not used, rather hydrogen is broken. So for that also energy will be required. So x will definitely be greater than y. So option number 3 here. Okay. Okay. Next, in case of decomposition of hydrogen molecule into 2 hydrogen atoms, the enthalpy of atomization is same as your bond dissociation enthalpy, right? Here whatever, because there is only one bond, whatever is the enthalpy of atomization, same will be your bond dissociation enthalpy. So option number A. Next, enthalpy of combustion, I told you it is always exothermic, so it will be negative. Now we will move towards the next thing, that is spontaneity and Gibbs free energy and equilibrium. Okay. So under spontaneity we will see enthalpy, entropy and Gibbs free energy. Okay. So first of all, what is a spontaneous reaction? So any reaction, any irreversible reaction which can occur by its own without any initiation is called as your spontaneous reaction. Many students get confused regarding spontaneous reaction and instantaneous reaction. Spontaneous reaction can be very slow, is nothing related with speed. Spontaneous reactions are only those reactions which can occur without any initiation, by its own it can happen. Okay. So there are two criteria which depends whether a reaction will be spontaneous or non-spontaneous. Okay. So means, for example, if you see water will always flow from higher altitude to lower altitude, right? That is a process that happens automatically. Ice melts automatically to water, but will water freeze automatically to ice? No, you have to keep it in fridge, right? So same thing, that is what some processes in nature happens by itself, whereas some processes in nature require some energy. So what are that criteria which will decide whether a reaction will occur by its own or you have to provide energy for that, right? So that is called as criteria of spontaneity, or the factors which will depend or which will decide whether a reaction is spontaneous or not. So the first criteria in that is your enthalpy. Okay. Spontaneity can be due to decrease in enthalpy. So it was found that many reactions, okay, where the enthalpy decreases, those reactions were found to be spontaneous. Okay. But there were many other reactions also where the enthalpy was increasing, still the reaction was spontaneous. Okay. So endothermic processes are also spontaneous reactions. So if you see in general, if I see, most of the exothermic reactions were spontaneous. Why? There is a very simple reason for that. Whenever energy is released, the system becomes more stable, right? So everybody wants to become more stable. So if I can undergo a reaction and become more stable by releasing my energy, so that reaction I will do by my own. Okay. So that is the concept here. So whenever we have any reaction where the enthalpy is decreasing, that happens by its own, because the system will become stable. But that is not that every reaction is following the same order. There were certain reactions which were taking energy and doing the reaction, but it was happening by its own. You do not have to initiate it. Okay. So that is, endothermic processes were also spontaneous reactions. So we can say that enthalpy is not the only criteria which can decide whether a reaction will be spontaneous or non-spontaneous, right? So that is why, to talk about or to decide that whether a reaction will be spontaneous or not, we have a second factor called as entropy. Now entropy is nothing but degree of randomness, how random, how disturbed, how you can say disorder the system is. So if any reaction is happening where the randomness is increasing, then we call that reaction to be entropy is increasing. Okay. So denoted by delta S, if in every spontaneous reaction the randomness will always increase, and the entropy, it is a state function, okay, it is denoted by state function delta S is equal to Q reversible by T. Okay, now delta S total is equal to system plus surrounding, and it is greater than 0. So for a reversible reaction, delta S increases, reaches a maximum value, and then at equilibrium delta S is equal to 0. So for irreversible process it is greater than 0, and for reversible process it is 0. Okay, this you have to remember. So now I have got two criteria that decides the spontaneity of a reaction. One is enthalpy, one is entropy, but none of them can individually tell you that whether it is enthalpy or whether it is spontaneous or non-spontaneous. So we need a criteria, or we need a equation which can combine both of them, both the systems, both the factors. So that is your Gibbs free energy, which tells that delta G is equal to delta H minus T delta S. So if delta G is negative, then reaction will be spontaneous. So finally we have got one condition, that is delta G, if it is negative, reaction will be spontaneous, and this is determined two factors, that is enthalpy and entropy. Okay, so if delta G comes out to be negative, then it is spontaneous. And we have one more formula for delta G related to equilibrium constant, that is delta G is equal to minus 2.303 RT log K. Okay, fine. Now we will do some questions here. Spontaneous reactions that occur are mostly dash in nature. So see, mostly it is exothermic in nature, mostly, but it is not always true that it is exothermic. Mostly it is exothermic in nature. Reaction is spontaneous if Gibbs free energy is less than 0 or it is negative. Okay. If enthalpy is positive and entropy is negative, what do you understand about the Gibbs free energy? So you can see, if enthalpy is negative, okay, delta G is equal to delta minus, and entropy is negative, sorry, enthalpy is positive is given, sorry, enthalpy is positive and entropy is negative. Okay, so I will get here delta H minus minus plus T delta S. So if you see, these are two, enthalpy is positive, entropy is negative. Yes, so I am getting two positive numbers. The addition of two positive numbers will always be positive. So delta G will always be positive, and it will be a non-spontaneous reaction. Next, calculate the Gibbs free energy for the reaction of the conversion of ATP into ADP at 293 Kelvin. The change in enthalpy is given to me, the change in entropy is given to me. Okay, so this is very simple. Delta G is equal to delta H minus T delta S. What is the value of delta H given? Enthalpy is 19.07 kilocalorie. So I will convert it into calorie, right? Minus T is how much? 293 Kelvin. 293 Kelvin into delta S is 90. Okay, so I have to solve this. 19070 minus 9 3s are 27, 9 9s are 81, 82 83, 9 2s are 18 plus 8 26. Get this value. So how much I will get? 26370 19070. Okay, so I will get 16 minus 9 will be 7. Okay, yes, so I will get how much? 7.3 kilocalorie minus, option number D here. Okay, fine. Calculate the Gibbs free energy for the conversion of oxygen to ozone at room temperature if the Kp is given to you as 2.47 into 10 to the power of minus 29. So if you remember, delta G is equal to minus 2.303 into RT. R is again 0.0821. Temperature is how much? Room temperature means 25 degrees Celsius, so 298 Kelvin, and Kp value is 2.47 into 10 to the power of minus 29. Okay, so little long calculation, but you have to take this one, log of K, right? This is log is there. So just do this calculation, and if you solve this, you will be getting around 163 kilojoule per mole. This type of questions are not asked in the exam, so I am not solving, but yes, this formula you should be knowing. Okay, So now let us solve some KCET previous year questions and see that what we have studied, can we actually apply them. So this is a question of 2022. The work done when 2 moles of an ideal gas expands reversibly and isothermally from a volume of 1 liter to 10 liter at 300 Kelvin is. So you can see isothermal and reversible process. So what is the formula for work done? Work done will be equal to minus 2.303 nRT log of V2 by V1, right? So let us substitute here minus 2.303. What is the value of N here? 2 moles, right? R value 0.0083. Then temperature is 300, okay? Log V2 by V1, 10 by 1. Log 10 by 1 means log 10 and log 10 is 1. So I have to solve this part, okay? So 300 into 2 I will get 600. Let me just take it as 2, okay? Let's not confuse too much. So 2.3 I am taking as 2, so 1200, okay? So 1200 into this one 0.08, right? So I can make it at 0.0. This 08 I am taking at 0.01, like approximation. So I will get around 12, right? So answer should be around 12. So that is option number C. With rough calculation I can easily predict the answer. Next, the reaction in which delta H is greater than delta U. This is very important question. So see, delta H is equal to delta U plus delta NgRT, right? We studied this one. Now I want that delta H should be greater than delta U. If delta H should be greater than delta U, see, delta H should be greater than delta U, means this value, this delta Ng value should be positive for that. Now see, you have a number and you are adding that number. One number is there and you are adding that one number to this number, then we are getting this number, right? Then only delta H will be greater than delta U. If this is negative, that means from this number, if you are subtracting this one, you are getting this one, and in that case delta U will be greater. So if I want delta H to be greater than delta U, delta Nj should be positive. Now I have to check for all the reactions. So here 2 and this side also number of moles is 2. So delta Ng, how to calculate? Delta Ng is equal to number of reactants minus number of products minus number of moles of reactants. So products I have 2 and this side also 2, so 2 minus 2 is 0. So I will get delta Ng is equal to 0. Here if I see delta, here number of moles of product is 1 and this side 0, so I will get 1 minus 0 and that is plus 1, right? So I got a positive value here, so correct answer is option number B. In the reaction given, heat of formation of SO2 is. So I want to form SO2, right? So if I want to form SO2, what will be my reaction? S plus half, sorry, not S plus half O2, it is S plus O2, okay? So I have been given with this reaction, okay? And if I just reverse this reaction, you see the first reaction is what? S plus 3 by 2 O2 is giving me SO3, okay? And I want to form SO2, so I want SO2 on that side and SO3 on this side. So if I just reverse this reaction, I will get SO3 gives me SO2 plus half O2, right? SO3 will get cancelled. 3 by 2 minus half O2. So 3 minus 1, 2 by 2, that is O2. So S plus O2 gives SO2. Okay. So now if I am reversing the reaction, then what happens to the enthalpy value? It becomes negative. So this is 2x and this is minus y. So if I add these two, it will become 2x minus y. So option number D here. Next, the ratio of the heat liberated at 298 Kelvin from the combustion of 1 kg coke and by burning water gas obtained from kg of coke is. Assume the coke to be 100% carbon. Enthalpies of combustion of C, CO and H2 are given to you. Okay. The ratio of heat liberated at 298 Kelvin from the combustion of 1 kg of coke and by burning water gas obtained from 1 kg of coke. Okay. So first of all, if you see how much heat will be generated if I burn 1 kg of coke? So 1 kg of coke means how many moles? See, the enthalpy of combustion of carbon is given, means this reaction value is given to me. How much is this value? 393.5. okay, this is 393.5. Enthalpy of combustion will be negative, so I will put minus here. Next we have, let's see the next question here. Bond enthalpies of A2, B2 and AB are in the ratio of 2:1:2. If the bond enthalpy of formation of AB is minus 100 kilojoule per mole, the bond enthalpy of B2 is. Okay, so again a very good question this one. So if you see A2, B2 and AB, I have this ratio, their bond enthalpies ratio. So what is it? 2, 1, 2. So I can make 2x, this is x and this is 2x. Okay. Now if the bond enthalpy of formation of AB, so if I want to form AB, I have a reaction like this, A2 plus B2 gives 2AB. Now see, the energy released in this process is minus 100 kilojoule per mole. That is for 1 mole of AB, but in my reaction I am getting 2 moles of AB, so the energy release will be minus 200 kilojoule per mole, right? So what I can do here is, see, the enthalpy of the reaction is equal to what? Bond enthalpy of reactants minus bond enthalpy of products. So this is what? Minus 200, okay, 100 kilojoule per mole, and we have here 2 moles of AB, so minus 200. Bond enthalpy of reactants, I have A2 and B2. So yes, sorry, not A2 and B2. So what is the bond enthalpy of reactants? 2x plus x, that is 3x, minus bond enthalpy of products, so that is again 2x. Okay, so how much I will get here? So just a minute, A2 is 200, A2 plus B2, right? 2x plus x is 3x. Okay, so bond enthalpy of reactants minus bond enthalpy of products. So I will get x equal to 200 minus 200, right? So what is the bond enthalpy? Means to break the molecule of B2, I will require 200 kilojoule per mole. That is option number C. Now here a question may think that ma'am, how can you get minus and here the option is given 200? So see, this x is what? X is the ratio, right? So whenever a bond breaks, we always get the answer in negative. Bond enthalpies are always, like whenever you break the bond, whenever you break the bond enthalpy, it is a endothermic process. Okay, we get endothermic process, but here what I am doing, here it is the formation enthalpy is given to me, right? So that is why I have taken a negative value here. The formation enthalpy means these are all your formation enthalpies are taken. So x will be your 200 kilojoule per mole, so option number C. Okay. Next, bond enthalpies of HH, Br, Br and HBr are given respectively, and you have to calculate the bond enthalpy of the enthalpy of the reaction. Okay, this is very simple. Two products. So in this bond enthalpy, reactants minus products we do. What is the bond enthalpy of H2? 433. Bond enthalpy of Br2? 192. Right? Minus 2 times of bond enthalpies of 364. Okay, so 3, 2, 5, 12, 4, 5, 6 minus 2 4s are 8, 2 6s are 12, 7 28. So I have 8 minus 5 3, 2 minus 2 0, 1 minus 103. So option number D here. Okay. Next, lattice enthalpy of NaCl is given and hydration enthalpy is given, enthalpy of solution. So I have given you this formula. Enthalpy of solution is what? Lattice enthalpy and hydration enthalpy. So it will be plus 4 kilojoule per mole, 788 plus hydration enthalpy. So this is a question from Comet K. For the gas phase reaction, PCl5 gives you PCl3 plus Cl2. Which of the following conditions are correct? So now you see, if you are breaking the molecule, you have to provide energy. So enthalpy will be positive in that case. So I can eliminate these two options. Now you see here only 1 mole of gases were there. Here we have 2 moles of gases. So randomness has increased. So entropy will also be positive, but here entropy is given negative. So correct answer will be option number D here. Next, when the same quantity of heat is absorbed by a system at 2 different temperatures T1 and T2 such that T1 is greater than T2, what is the relation between delta S1 and delta S2? So if you see, the formula of delta S is Q by T. Okay, if this temperature is high, then delta S will be low, right? So as T1 is already higher value, so delta S1 will be lower value. So delta S1 will be less than delta S2, and that is your option number D. Okay. Next, the correct statement regarding entropy is, at absolute zero temperature, entropy of a perfectly crystalline solid is 0. Yes, that is a correct statement. Next, and at absolute zero temperature, the entropy of a perfectly crystalline substance is positive. No, it is 0. At absolutely zero temperature, the entropy of all the crystalline substances is 0. No, it is only for perfectly crystalline substances. At 0 degree Celsius, the entropy of a perfect crystalline solid is 0. No, it is not at 0 degree. It is absolute zero temperature. So option number A here. Next, reaction has both delta H and delta S as negative. The rate of the reaction. So this is a very simple question. See, the rate of the reaction, rate of the reaction is always dependent on the temperature, okay, nothing else. So the rate of the reaction will increase if you increase the temperature, right? We have studied in chemical kinetics that rate of a reaction is directly proportional to temperature. Okay, if you increase the temperature, rate will increase. So students, these were the most important topics, formulas, concepts from the chapter Thermodynamics, and I hope that if you just watch this video and write down all the formulas, then this chapter is done for you. Just practice some questions with this, and if you have any doubt, please put down in the comment section. I will definitely address to it. So thank you for watching, and do not forget to subscribe the channel, because we are coming up with many more important videos. And very important, your exams are very near. Please do not waste time. Study hard, focus hard, work hard, and do smart study. Okay, all the very best.